Okay, Assalamualaikum. We'll continue our lecture in this topic, Fire and Explosion Part 1. Okay, this is a flammability of gases and vapors. The main thing that you need to know is a flammable gas burns in air only over a limited range of composition, meaning that they have a specific composition in order for them to get ignited to continue burning. In other words, the vapor air mixture will not burn when the composition is lower than the lower flammability limit, or you call it as LFL. In other words, it calls the mixture is too lean for combustion, meaning in order for the combustion to happen, the level of vapor X mixture has to exceed the lower flammability limit, LFL. That's the minimum level. Well, the mixture also is not combustible when it's too rich, too much. When it's too much also, it will not be combusted. Okay, so it has to be, if it is above the upper flammability limit, you call it as a UFL. So in order for the combustion to take place, the range has to be between LFL to UFL. All right, anything below LFL or over UFL, it will not be combusted. So that's the rule of thumb that you need to know, right? So a mixture of flammable when the composition is between LFL, as I mentioned just now, right? Okay. So this is basically a general way to represent a flammability gas vapor in a triangular diagram. I'm sure most of you are quite familiar with the triangular diagram. This is the axis for oxygen, methane, nitrogen. Okay, so consider example point A, this point. Okay, represent a mixture of composed 60% of methane, 60% of methane, okay, 20% of oxygen, and 20% of nitrogen. All right, so point A is not flammable. Okay, because this is the upper limit of pure oxygen and this is the lower limit of pure oxygen. So in order for the combustion to happen, it has to be between this triangular diagram, which is between this UFL and LFL. So since A is outside the region, so A is not flammable, meaning that with this composition, 20% oxygen is not enough to be combusted, right? So this is how you check whether the mixture of gas is combustible or flammable or not flammable. So one of the things that you can see by using this triangular diagram, right? So as I mentioned, in this green area, the mixture are flammable. This is a stoichiometric line represent all stoichiometric combination of fuel plus oxygen. It's a stoichiometric line. Okay, this is the air line, represent all possible combination of fuel plus air. The air line intersect at the nitrogen here at 79% nitrogen, 21% oxygen, which is the composition of pure air. So this is for pure air. And this is the limit oxygen concentration, where minimum oxygen concentration required to propagate a flame. This is the limit of oxygen. All right. So below LOC, the reaction cannot generate enough energy to heat entire mixture of the gas mixture. So flammability limits for vapors will determined experimentally. All right. So each of the vapors will be determined by experimental. For a mixture, LFL and UFL are computed using Le-Chatelier equation. This is a Le-Chatelier equation. If you want to, you have individual LFL or you have individual of UFL, not a mixture. Okay, you want to calculate the new LFL of mixture, right? So this by using this equation, the Lee-Chatterley equation, which is, for example, for to calculate LFL mixture is equals to 1 over summation of yi is the mole fraction of component in I over that particular component of LFL plus YA over LFLA plus YB over LFLB. If you have 5, so until Y1 to Y5. So by adding everything, 1 over the summation, so we'll get the LFL mixture. The same goes to UFL. Okay, we use some example. What are the UFL and UFL, LFL and UFL for mixture gas composed of you have 0.8% of hexane, 2% of methane, 0.5% of ethylene by volume. So you need to know what is the LFL mix and UFL mix. We can know what is the LFL and UFL for each hexane, methane, and ethylene. Okay, and from that LFL mixture or UFL mixture, we can determine whether this mixture is it combustible or not. Is this mixture is combustible or not? So we need to know the LFL and UFL mix. So we make it in the table. Hexane 0.8%, methane 2%, ethylene 0.5%. So you total up, you have the total combustible is 3.3%. Okay, you know all these three is a combustible material. So total combustible material is 3.3%, and the balance is air, which is 96.7. So you calculate the mole fraction. You got 0.24. You have to know the molecular weight. 0.61, 0.15, and these are given in a table in the appendix. All right, these are given in the appendix. For example, hexane, the LFL and the UFL, and the same goes to methane and ethylene. So by using equation 1.2, the LFL mix is 2.6%. This equation 1.2. Using this equation, 1 over Y methane over LFL methane plus Y ethylene, okay, like this. So this is a mole fraction, right? So LFL mix equals to 1 over Y1 0.24 over the LFL 0.6 over 5, 0.15 over 2.7, and 1 over overall of this, summation of this. So you get alpha mix 2.65% by volume or total combustible. Okay, and then to get UFL mix, you use equation 1.3. The same procedure, you get 10.0% by volume of total combustible. Okay, so can we know from here, does this mixture is combustible or not? Is it combustible? So how many total combustible? Is 3.3. From this range, can we say, is it combustible or not combustible? So 3.3 is between this, right? So it's between 2.65 to 13.0. So from that, we can conclude that the mixture is flammable. So this is how you determine the mix, the LFL mix and the UFL mix, right? In other way, there are a few ways in order for you to calculate the LFL and UFL. For a hydrocarbon vapors, the LFL and UFL are a function of stoichiometric concentration, CST of fuel. So LFL is 0.55 CST and UFL 3.5 CST. Normally, CST the volume air in fuel plus air normally is given. Right? So this is an example of hydrocarbon going through a combustion. Right? This is the stoichiometrics. You have M, X, Y, Z, and M. Okay, no, right. So in order for you, by using this stoichiometric equation, you can calculate the flammability of the hydrocarbon. Okay, I'll skip this through. I just want to go straight away. This is more to derivation. I just go straight away on the equation. Right. To calculate the LFL, you will use equation 1.6, providing that you know M, X, and Y in the equation. The same goes to UFL. You know M, X, and Y in the equation. Let's go for example. Estimate LFL and UFL for hexane and compare the calculated limit to the actual value determined experimentally. Right. So this is the stoichiometric combustion. You have C6H plus M X ZO2 MCO2. So you say M is given 6, X is 14, and Y is 0. So using equation 1.6, you get LFL is 1.19 and UFL 7.57. So you can compare this value with the flammability data in the table appendix as well. LFL is based on fuel in air, how much fuel in the air. However, oxygen is the key ingredient and there is a minimum oxygen concentration. You need to have a minimum oxygen concentration required to propagate the flame. That is called LOC. Okay. So how to determine the LOC? The LOC is a Z, is a constant times the LFL. Example, estimate the LOC for butane. If you have butane, okay, how do you, the stoichiometry of butane combustion is here. So the LFL for butane is 1.8%. So the LOC is 1.8 times 6.5. So this is 6.5. 6.5 equals to 11.7% of oxygen. So you need to have a minimum 11.7% of oxygen. All right. This is just a relationship between flammability properties. You can just read through this. All right. This is a tutorial. After this, I would like you to do this tutorial, estimate the LFL and UFL of the following mixtures: methane, ethylene, acetone, ethyl ether, total combustible, and the air. So this is the needed LFL and UFL data from Appendix B. All right, that's it for our first part of the fire and explosion. So we will continue on our next class for fire part 2, fire and explosion part 2. With that, thank you very much.